But this is our standard 101. We're going to go through and just gently introduce you to JavaScript, or at least the small subset of JavaScript that you actually need to know to stitch together your Earth Engine questions. This covers the syntax. And then we'll slowly build up to an example of putting together what Katie was referring to earlier, this composite of NDVI, normalized difference vegetation index. It's plantiness. It's a ratio of 2 of the spectral bands, which really highlights and measures the amount of plant matter in a particular pixel. That's the idea anyway. Higher values are more planty, lower values are less planty. Yeah, so we will start out with some of the JavaScript things and just slowly work our way up, touching the different parts of the code editor and covering the different pieces. I've never done this non-visually before, so it's exciting. All right, does everybody have it open that wants to have it open? Or can everybody look on a neighbor? Is anybody stuck? I'm just going to keep going. So the JavaScript, you only need to know a handful of constructions. JavaScript, if you've written code in R or in Python or in any other kind of like scripting language, nothing is super surprising here. The JavaScript is only being used to build these graphs, to build up these computation descriptions. So one key thing is you need to start your declarations with var, declare your variables with var. The code editor will complain if you have an undeclared variable. Second, we talk about objects. So I'm really trying to remember this script here. Oh, all right. How close was I? Yeah, not bad. I think we're good. This is sorted? Halfway. That was an unenthusiastic. Okay. Just go. We'll make up for lost time here. Okay, declaring variables. We have numbers, we have strings, we have dictionaries, we have lists. None of these are particularly sophisticated or mysterious. You can access elements in a dictionary by using this dot referencing, and we can print out values which get written to the console. For each of these scripts, and so I'll put the, thank you, by the way, to the tech folks. We run this, and we get some outputs. And you can see in red here, we have a problem. Our problem here is that number is not defined. Anybody, for 1 point, tell me, how do I fix this? What do I do? What's wrong? This is interactive, in case you didn't. All right, I'm hearing what sound like 3 or 4 of the right answer. It's not defined. We haven't given number a value. Here, I suspect the problem is that we want to call this variable number. Number, okay. And we run, and we get outputs in our console. Earth Engine in the code editor is handy because if we run and we get outputs to the console, you'll see we have this highlight here, which shows us there's information, there's output there that we need to address. Okay, just showing you the different pieces of the API. So we've got our scripts, we have our scripts pane, which is where we're interacting with the code, and then we have our map down here, which we haven't touched yet, but it's going to be important. Okay, any questions on this? This is basically it. You can see that comments are formatted with these double slashes here. All right, we'll go quick. Sorry, I did that very quick. Anytime you make a change and then you load a new script, it will prompt you, hey, there are unsaved changes. We don't want you to lose your work. I've gotten into the aggressive habit of saying, no, I don't want to abandon, or yes, I want to abandon changes. So there are 2 kind of computing paradigms. There's 2 ideas that we really want to cover here. So this is example 2. And this is showing you the wrong way to do something. This is using a bunch of JavaScript functions to compute this average day of year of harvest. So let's say we have this list of dates, which are when we harvested a particular crop. And we want to find out what the average is. we can use built-in JavaScript functions like new date or math.floor to compute these numbers. But that's not the Earth Engine-y way to do it. When I run this code, all of this code runs in the browser. And so this is when we talk about the difference between the JavaScript and the Python, the browser here is running, browsers speak JavaScript. And so we're running the JavaScript here, and this isn't touching Earth Engine at all. So the broader theme here is that we have a client, which is this web page, this pane, my laptop here, Katie's laptop really. And we have the server, and that's this set of machines, it's this service that's running in Google. And so here this is client-side processing, and this means that you have to know JavaScript, and you have to understand the behavior of the date object, and it will behave differently in different browsers. We ran this when we were in Singapore, and we got a different answer because we were on the wrong side of the date line. It was complicated. The idea with Earth Engine is we want to separate ourselves from having to rely on the JavaScript details. And so we can work with Earth Engine code just using JavaScript as the glue to stitch these things together. And really insulate ourselves from the implementation. So we can run on Earth Engine, and within Earth Engine, our results are guaranteed to be consistent across machines and across platforms. How you're calling it, you pass your question, and you get the same answer back. Okay, so I ran that, and I got 234.75. Here's a slightly different way of doing this. So here this is a loop, a for loop. If you've written any amount of code, you know for loops. This is a structure that you use to loop over this list, and we do a thing for each element in the list, and we have our aggregator sum, and we print out the result of that sum. Earth Engine doesn't work with for loops. We work, the Earth Engine client libraries are really functional, and there is it might not happen here, so don't feel bad, but there's a click that needs to happen in your brain for you to understand how functions can be passed around as data. So we're gonna work through that. I just want to say it now. Functions can be data. We can reference a function and pass it to something else. And so that's kind of what we're getting at here. So we're starting with these dates, and we're defining a function. And we're still doing all this JavaScript goofiness. We're still building up this description of just doing the computation in the client. But here we make a function, and we do the same thing. We're for looping over this list, and we're just calling our function. So the syntax with the parentheses, we're passing in an argument, and that becomes date up there, and we've pulled out bits of the logic and separated it into a function. Anybody lost? No, I'm doing a great job. Okay. Here is the Earth Engine way of doing this. And maybe, sorry, just so I stay believable, keep me honest, we're going to run this code again. We get the same answer. We separated our logic out. Here, we are constructing a list, and you can see there's a little more happening here. There's less code, but there's more happening. This is a list. It's an EE list. Anything that starts with an EE is an Earth Engine object, and that's a handle into an object on the server. It is a way of referencing server-based structures. This is something that happens on the server. So I have these numbers here. This is a JavaScript list being passed into ee.list. And here, this is an Earth Engine object. We can print this. If we print dates here, we see that it's a list with 4 elements. But this is something that lives on the server. And as such, we can manipulate it using the server-side processing. So when I call functions on this, when I manipulate this list, it's actually the expressions, the results are coming from the server. This is no longer client-side. Katie's machine is no longer actually doing the processing. It's building this description, and it has this EE list reference, goes to the server, is manipulated on the server, and we get back our results. Okay? And so we have a function, and we return the date, and we get a relative date. And I prefer this. I don't really know JavaScript that well. I'm not a JavaScript expert. This, to me, is easier because this is exactly the same in Python. This is exactly the same in every Earth Engine script that you look at when people are doing server-side manipulation of dates. They're using these date functions. And those show up here in the docs pane. And so we can look, and there are all sorts of date functions that we can use to manipulate these date objects. So this function takes a date and returns a number. And what we're doing is we're taking our list, and we're not doing a for loop. Because a for loop, if you remember the comment about bags, and keeping things in a bag structure so you don't have order, a for loop requires order. You have to 1, 2, 3, you iterate through that list. Here, we're saying for everything in this dates list, just map it. Just do this function and replace all of the input dates with the outputs of that function, and then reduce. Question?
Can you kind of tease apart a little bit the return function? So I see there's an EE date.
Yes.
And then but there's like another function that says get relative.
Yes.
You already have the dates. What do you need to?
Yes, great question. So this list, we construct these EE dates here. The things inside of the list are actually just strings. And so we have this set of strings. So we're doing a little magic here. We're moving our hands quickly. The strings go into this function. So we have, these are just strings. They go into this function. This function takes a string, passes it to the EE date, and then we get out this relative. This is just a number. This returns a number. We can look at get relative here. And pop out the docs. And it returns a value between 0 and 365. And we can specify the units, we can get the relative month, we can get et cetera, or yeah, right here. Okay? And the reducer we're using, so this is our sort of intermediate representation. So dates.map, day of year. We have the strings that go in, they get churned through this function, and we get out these relative day of years. Then we can reduce that list. So this is doing exactly the same thing as the line above it. We're just subsequently calling reduce with this mean reducer. So we get the average. Question? Correct. Yeah, so this EE reducer is a server-side reducer. And this whole idea that we have these server-side objects that we're manipulating, it feels a bit like magic. We're controlling something in Google's infrastructure using these short references. But it's really handy because we don't need to have them locally. All of this processing can be done, and we can actually crack open the list, that graph of computation, and we can look and see, oh, here's where the reducer is specified, and here's where the days of the year, the input strings are specified, and we can see all of that. It's not useful to show it here because it's just a big blob of JSON, JavaScript objects, but it's there, I promise. Question?
How can we tell that this is JavaScript and not Python? And is this real JavaScript or it's some, because I don't see any semicolon at the end of the line.
Yes, the question is it real JavaScript? Yes, so this is a flavor of JavaScript called ECMAScript 5, ES5. It's not the most modern JavaScript. It doesn't have all the bells and whistles of new. If you're like a person who builds websites for a living, you're not using this version of JavaScript. It's perfectly valid. Browsers understand it. We just haven't updated the code editor to use this latest and greatest set of syntax. But yes, it's real JavaScript. The question is, how do you tell the difference between Python and JavaScript? And it's awesome because there's only a handful of differences. We try to make it, because you're working with Earth Engine objects, these EE dot objects, I don't need to know Python date manipulation. I don't need to know JavaScript date manipulation and how it differs between different browsers. I'm insulated from that, And really, to convert this to Python, I just have to change a couple of syntax things. I change the way that dictionaries are declared. I change the way, I don't use var in Python. Function declaration is a little different. Someone wrote a tool, it's called GEE map. It's by Qiusheng Wu. You can find it on GitHub, and it automatically converts JavaScript to Python just for Earth Engine. In general, it's a difficult problem, but most Earth Engine scripts, if you squint, you can convert between the two languages relatively easily. I do that all the time. I am fluent in Earth Engine, and I am not that strong in JavaScript or Python, but it's relatively easy to convert between the two. We are burning through time here. Okay, let's roll. Okay, so that's map, reduce. Here, you see I did it real quick. I changed the sum, just so we get the sum of that list. You're free to pick from any of those reducers that Katie highlighted earlier. And you can see we have all the docs here to pick through the details. Count and first, and how many things go in, and produce a histogram of all the numbers that I saw, and give me the first value that isn't null, or give me lots of different options for reducing lists, images, feature collections. Okay, let's move to number 2. That was only number 1. Okay, here we're gonna reference some data. So the way that you access data, you don't download the data and use it in the code editor. Again, it's a hook. I'm referring to data that exists somewhere else. So here, I want an SRTM data set. This is the shuttle radar topography mission. I could just search elevation in the Earth Engine data catalog. But here I'm pulling up a data description page for SRTM. And we have a little snippet here. We can import the data. I'll choose to import it here. I'll click this import button. There's a full data set description on that page that gives you everything, license, all the values that you can have, the different bands, the projection resolution, et cetera, et cetera. But here you see I get an import record. This is an image. It's a variable named image. This is a variable that I can use in my script. It's declared up there. It's separate. It's ethereal. I can just use it in my script. We call this the preamble. And it's just a way of separating out some of these imports and these declarations from the rest of the script. So I can use the code here. There's this little mysterious blue box to show the generated code. This is exactly equivalent to the line here. Okay. Okay, so we can add this to the map. Let's do that at least. Everybody following along? Anybody stuck? Folks standing at the back of the room, does everybody's screen look like this? Yes, it is part of the code, but it feels a little bit separate. We call this, the imports pane or the preamble. So what you can do is you can hover over one of these items here. If you just search for SRTM, you can just import one of these. And I can import the same data set again, and it will be given a sequential name. Okay, or I can write just the code here. Okay. So we're going to use a function called image.where, and this is tricky. So you see we have this image here. It's not very pretty because it's not stretched. You can see there's some subtle variation. There's a lighter patch here, but it's just stretched according to some default visualization. Question?
What is the shortcut you're using for uncommenting them?
Question about the magic. Yes, so there's a shortcut. If I'm on a Mac, I can hold Command and then slash, and that will comment and uncomment. I think it's Control slash on other platforms. And that's a real handy tip. We also have, while we're on the subject, if you type a dot and then whoa, not on here. No, can't do it. Maybe you can. We'll do a bit of autocompletion. It's not super sophisticated autocompletion, but we try to, whoa. Oh no, this is embarrassing. Yes, if you type a couple characters and then hit Control space on a Mac, and I think Control space on other platforms as well, it will do a bit of autocompletion. Okay, so image 0. Can anyone tell me what the projection or resolution of that image is? Don't all shout at once. Heard something? No. There. Of image 0. Just I declare an image as a constant image. It's 0 everywhere. I add it to the map, I always get 0. It is whatever you want it to be. What does that mean? Earth Engine, remember, we're being driven by what the output projection is. Everything is getting reprojected into that output projection so we can do our computation in that output projection. So when I have an expression like image 0, and then I do a bunch of other stuff to it, that gets reprojected into these tiles that I see in the map, and we're happy. Okay, so you don't need to think about this. This is a very Earth Engine-y shaped concept, and that's why I'm burning precious time on this. Is because we really there is no intrinsic projection there. It gets reprojected into whatever the output projection needs to be. So here, what are we doing? Let's just quickly rip through this. I'm sorry, we're going to have to go quick. Here we have a handful of where statements. Where elevation GT is greater than, you can look in the docs, where the elevation is greater than 200, set the value of my image to 200. Where the elevation is greater than 400, set the value to 400. So each time we're getting a new image, and this is a very Earth Engine shaped expression, we're chaining methods together. So we're not saying var intermediate, var intermediate, var intermediate. We're just calling one after another these function calls. Okay? So we wind up with an image that has these 4 different values. We have values 0, 200, 400, 600. And then we update the mask. The mask is the alpha or the transparency associated with each pixel. And so we take that mask and we say anywhere where the value is greater than 0, set the mask to be valid. Greater than 0, if it is greater than 0, that will be 1, and that's true. Update the mask, make it valid. Okay? So now we have our image that we add to the map. So we have a map, capital M map. Capital letters refer to pieces of, in this case, the code editor. If you're in Python, you don't have a map because you're just working in a Python notebook, you're working in a Python environment. You need to bring your own and define your own map. And so that's what we're looking at here. We're taking the map and we're adding a layer to the map. Here, we just provide some visualization options. So we have 4 different values, 0, 200, 400, 600. And those are our 4 values, blue, green, yellow, red. Okay? And what's cool is because this is a global image, we can zoom and pan anywhere, and we're getting the values for each of these tiles in that tile separately. You can think about these being sent out to different machines in Google's infrastructure. Okay, so this is like not a super like fun or pretty image, but we in 7 lines of code got this output. Okay. All right, we'll keep rolling. Any questions? No. Cool. Okay, let's do something bigger. We have 18 lines of code, and we have we're selecting, just at a very high level, looking at this, we're getting a region. We want a particular state. We are getting an image collection, and we're filtering down the date and to a particular region, and then we're reducing it. We're computing from the filtered collection, computing a median value for every pixel. So our output is the median of that stack of images at every single pixel, and we're going to clip it to that region. So we try to run this, and what happens? Well, stuff isn't defined. We have to import more data. Luckily, someone gave us some breadcrumbs here, and we need to import tiger states. And we have a couple different versions to choose from, 2016 or 2018. Let's go with whatever's more recent and call it Tiger. Okay. And so here we have our tiger.filter. Run it again. Oh no, our image collection isn't defined. So now I have to go to Landsat 7. And these are like, Tiger isn't that big. It's maybe gigabytes of data. Landsat collections are petabytes. And so we're referring to this, and we have a very inexpensive way to refer to this. It's just the name, Landsat collection. And we'll do the, collection 2, tier 2, why not? There is all sorts of science that determines the differences between these different products. They're at different levels of quality. Tier 2, collection 2, is not the best stuff. Maybe we want to go with collection 1. Okay, I won't search for it. I'll try not to be fancy. But just know that there are different versions, different flavors of each of these collections. Okay, and sorry, I imported the wrong one. I think we want the raw scenes. Raw Landsat 7. Okay. Let's try that. Okay. So, you all can watch me debug this in real time. We're getting an error. The error is complaining that image.select, and I've maximized my screen size here. I've zoomed in a bunch. The pattern B3 isn't matching any of the bands. And so I'm looking, and I'm seeing that we have this clipped composite, and we're down on line 17, trying to select off 3 of these bands. And I'm referring to them by name. I can go and look and see what the band names are for Landsat 7. Here, what I suspect is, oh yeah, we're looking at the wrong date and time. We don't have any imagery here. Why don't we have any imagery? This one's subtle. I highlighted it here. We're filtering. Yeah, we're filtering for a state named state. Okay, so we have 0 states with that name. Earth Engine happily gives us an empty collection, and we're trying to filter that. When we filter and we select, we don't have any bands. So let's look at, what is the shortest name I can spell here? Ohio. All right. Great. Everybody on board? That looks like garbage. This is because we're using the raw scenes. The raw scenes, there's very little filtering that happens. Let's look at collection 2, tier 1. Top of atmosphere. Okay, sorry, I'm playing around. And this honestly is highlighting the dynamic nature of developing an Earth Engine. This rapid development, I can look at the results of doing this computation and try out different filters super quickly. Question? Absolutely, yes. One of the early criticisms of Earth Engine was, oh, great, now people can make 1 million crappy maps. Please don't make crappy maps. The bar is lower. I think that is there's a kernel of truth in that criticism, but really we exist in order to make these scientifically defensible products easier to create, to reduce that barrier. But there is a certain amount of responsibility that comes with that in terms of understanding the data that go in, the methods that are used. There are plenty of papers talking about strategies and approaches. Please do ask questions and lean on bodies of knowledge for doing defensible and realistic work. Okay, I am going to get off the soapbox for a second. We're just going to throw more data at this problem. I have increased the amount of time here from 2010. This was 2010. This is now 2011. So I'm using 15 months of data. And it is better. You see, it's a little bit transparent. This is because of a problem with the Landsat 7 sensor. If we were to use Landsat 8, we would have probably a cleaner view here. But you can see we're starting to get rid of some of those clouds. That's the idea of median filtering. And this is nice because it speaks a bit to how you don't necessarily have to have a sophisticated compositing algorithm if you have a lot of data. And so you can rely on things like law of large numbers, the fact that clouds and cloud shadows move around in order to generate these composites pretty quickly and easily. Whew, we are going to have to go so fast. Okay, any questions about filtering collections? We have all of the metadata available from the providers, and we try to make it very easy for you to filter down collections and composite them. Okay. This one is really just showing, you can go to this TinyCC link and download this Florida Water Management District set of polygons, which will enable us to, oh, super. Katie did it already, maybe. Will allow us to import our own data. So the mechanism through which we do this is this assets pane. Assets refer to images that you own or tables that you own, and it's like Gmail or Google Drive or Google Cloud, where you upload data and they're private and they're personal and they're non-discoverable unless you choose to make them so. And so what we can do is we can add new data. We can choose to ingest a shapefile. In this case, this is a zipped set of shapefile and sidecar files. We can upload the file that we downloaded, choose a name for it, and we're off to the races. I'll see if I can do it live here. You all see this? Don't see this? Yes. Okay. This is just highlighting the tasks over here. So way back an hour ago, we talked about having the batch and the online stacks. Remember the different computation environments? Tasks are the batch environment. Tasks can run for days. Tasks can run for up to 10 days. This one should run really quickly because it's just ingesting a small amount of data. But this is how we specify tasks, processing that lasts longer than just our browser session or longer than a 5-minute request. So this will run if I close, if the power turns off in this building and we all get disconnected from the internet, this task will continue to run on the Earth Engine servers. You saw before it said unsubmitted tasks. That's before that state is true. So that's when it's running locally, it's uploading all the data, et cetera. We can click on this, we can get more information about the task. We can look in the Earth Engine Task Manager. And look, it says it's completed. We're just waiting for this UI to catch up. We can refresh. And here we have our water management district, eventually. We have our water management districts. And this has a little thumbnail. It describes the properties of all of the features. Okay, so that was just pulling in a shapefile, super easy. If we want to share it, we can click on any of these share buttons. I trust you all to navigate that. But we can refer to it the same way that we refer to any other data in the Earth Engine system. So we can go here. There's this little arrow when I hover over it. Or if I click on this, I can choose import. Again, I get an import record. I'll delete this previous reference to a table. And I'll run this. And these are our Florida water management districts. And this has been an example we used for a long time, but now this is particularly relevant given all of the terrible stuff post-Hurricane Ivan that's been happening in Florida. Okay, and we can use this, again, just like any other feature collection in the system. We can do our processing and refer to this using the same EE feature collection hooks that we have from earlier. Okay, I'm gonna keep rolling right along. This is probably the most difficult to understand. I'll apologize, I'll go very quickly through it. Essentially, we're taking the Sentinel data. So remember, we had the Landsat data, we had Sentinel data. Sentinel-1 is radar, Sentinel-2 is optical. And so we're going through, and each of those data products comes with an associated bit mask. And you have to do some shuffling here. I don't love this example because I feel like it's a little complicated. But essentially what you're doing is, or what we're trying to demonstrate here is that we have everything, if you want to go way down into I'm looking at individual bits and the values of those bits and changing the pixels and visualizing them based on those bits. It's possible to do in Earth Engine. And it's the same set of logic. We build our graph, we have our reference to the collection, we filter it, and we map this map S2 clouds function over it. And so what we wind up with is an image collection. So we have an image collection, we're filtering, filtering, filtering. As a result, we have a map operation, and we map. Sorry, as a result, we have an image collection, and this function accepts an image and returns an image with an updated mask that is normalized to some set of values. These values here are kind of magic values. You pull these off of the dataset description. But this is going through and cranking out, going over this collection, and then at the end, we composite it. So we can add the layer to the map. This is just setting where we're looking. Add the layer to the map, compute the mean, clip it to a particular region, so exclude pixels outside of a region we've defined, and then visualize it. Okay, and we can run it, and we can see this happening. This is cool because this cloud masking operation is using the quality bits that the data provider provides. And they're not perfect, but they're good enough if we use a lot of data that we can get a nice composite out. And you can see this composite is defined and zooming in and out, and it's just Earth Engine is recomputing the values that go into it. Okay? All right. Any questions? Yes?
Is the order of the filtering, is that optimized in the back end so we don't have to worry about that? Or I guess like another way to phrase that is like if we rearrange this, like is there going to be any performance improvement?
Yeah, the question is, does the order of the filters matter? Do we want to front load the selectivity, have the selectivity come at the end? It shouldn't matter. If I and my coworkers do our jobs right, it shouldn't matter. There are some cases where it does. I realize that's a really frustrating answer to give. Most of the time, it doesn't matter. Most of the time, if you're doing kind of the standard set of filter by time, date, location, metadata, whatever, most of that, we have a process we call filter propagation. We push that down as far as we can so that when we're reading data from disk, we read a minimal amount. It starts to get complicated if you're doing things like joins, where you have a collection A and collection B, and you're cross-referencing those collections and matching, and then you filter the results of that. Those are harder for us to manage, but our goal is to make it so that often, I would say 99% of the time, you shouldn't have to worry about the order of filtering there. Great question. Cool, okay. This is quick. Not my fault they scheduled an hour. It is a little bit. Okay, so we can do a similar thing. These processes are very, very common. To want to take a collection, filter out the clouds, and build a composite. So common, in fact, that we have for Landsat a simple composite algorithm. So you can find this in the docs. But essentially, this is an Earth Engine algorithm that takes Landsat, and it only works on Landsat, and it composites it, basically doing the same thing, looking at the cloud quality bits. This is to make it easy to get composites without having to do the bit shifting and the bitwise operations to extract the provider information, the quality flags, from the data set and kind of reapply them. Make sense? I see some nods. Okay. So I just ran this, and you can see we have our nice composite. And so if I wanted to like generate this from scratch, not using Earth Engine, step one would be to go download all of these images, figure out how to composite them. I would only be able to do that for my region of interest. If I suddenly change my region of interest or change the zoom level that I want, I would go start the process again. But here I can go literally anywhere that Landsat, the collection is defined. Here we're looking at 2 years of data, so it's very likely that we have data which are present in all of the locations that we're looking. Question?
Well, that was my question. If the composite was for a certain date or year.
Yeah, so we're just filtering down to all images that fall within this time window. So this is 2 years. Just taking them and smacking them into our simple composite algorithm. Simple composite does some things like, removing the clouds and stretching it, making it visually and honestly scientifically valid. It is not the most simple. The name hopefully holds a lot of weight. It is not the most sophisticated compositing algorithm. It's intended to be quick and to give you data that you could then use for training a classifier, building a base map, doing a quick thumbnail visualization. This is maybe not what you want to use if you are trying to really squeeze out every pixel over a super cloudy area. You may want to build a more sophisticated time series analysis. Okay, I am gonna go faster here. We have NDVI. This is the metric that we've been talking about. We like it because it's a simple metric that's very easy to understand. Vegetation. So higher number, more vegetation, lower number, lower vegetation. And the way that you generate NDVI is just this formula here. You take band 5, near infrared, minus the red, over near infrared plus the red, and that's your expression. That is, it goes back 50 years or so. It's a very well-established metric for generating this normalized difference number. We do that for each pixel. And so here, we're just getting everything set up. We have our Landsat collection, doing the same thing, filtering. We have our composite. We build a composite. And the composite we're only looking at red, green, and blue, right? When we look on the map, we just see the red, green, and blue bands. That's what this call is. Band 4 is red, 3 is green, 2 is blue. We're looking at red, green, blue, and we have all of the other bands available. So we have this near infrared band that's there, and we can use for computation and subsequent visualization. So here we're taking our composite, we're just selecting off some of the bands, and I'm going to show you 3 different ways of computing a statistic for these pixels. Step 1, method 1, strategy 1, approach 1 is just to use the Earth Engine functions subtract and divide and add. Can anyone tell me why I'm not using like a plus sign and a minus sign and a division sign? Yes, heard it in the front. They're not server-side functions. Those are things, yeah, you had it. I know you had it. Those are only defined, those are going to be JavaScript plus minus divide. And we're not working with JavaScript numbers. These are references. These are parts of a graph, and we're calling divide. And so divide takes 2 parts of these graphs. It's a complicated way to think about it. I want to recognize that. But really, yes, this is different from a client-side operation. Okay, so this works, and this works great. Sorry, okay. I'll run this, and we'll get our nice map, and we have a palette where we're stretching between -1 and 1. This is kind of the minimum value that we expect and the maximum value for this index. And we linearly interpolate between all of these palette colors. So -1 is black, green is 1. We set the opacity so we see a little bit transparent through it, and we set it as a map layer. Okay. and you can use colors here. You can spell out the color names in CSS. You can do the 0000 for black hex color codes. And this, again, anything that happens on a capital M map is controlling this map. So you can see we set it to satellite mode instead of the underlying map mode. Okay, and that's just for visualization. All right, so that's our first method for computing this NDVI image. If I comment this out using my handy dandy trick here, and I have method 2. This is image.expression, and this is we recognize that line 38 is a lot of typing, and I find the strategy on line 38, the sort of method-based approach, it's harder to make mistakes because you have to spell out all of this, but it is not what you want to use if you are implementing some scientific algorithm that has 10 different variables and a lot of operations between them. This is, I'll call it a bonus programming language inside of Earth Engine. So this is our numeric expression language, which lets you define variables. Here we've defined b5, little b5 and little b4 to be these composites. So we're selecting off these layers, and then we're manipulating them in a way that feels like JavaScript, feels like Python, feels like R. But it's actually different from all of those. This is a string which gets passed to the server and executes on the server. This is way more succinct, way more terse. It's a shorter way of writing it, and honestly, it feels more natural. So again, if you have a scientific paper that you're referring to, this is an easy way to get it to match visually. The catch, of course, is that this is just a string. So there's no error checking. This won't tell you if you did something funky. You'll only know about an error that you made here at runtime when you actually pass the string to the server. The server tries to process it and tells you, hey, maybe you had a weird character in here, or a variable you didn't define, or yeah, you see here, you get a little red if I just mess this up. Okay? So we're talking about just the trade-offs between the different strategies for defining for doing our math, really, our pixel-based math. And you see if I run this, I get exactly the same result. The third method is just a baked-in normalized difference function. Again, these are very fundamental remote sensing operations that we're doing, processing that we're doing. And so normalized difference, 50 some odd years old. This strategy is baked into Earth Engine. So we have image.normalized difference, where you specify the bands that go into the processing, and it just does that set of ratios. Okay, so which one's best? Correct, they're all great. You would use different strategies in different scenarios. If it's baked in, that one's probably the best. If you want to be very explicit, the first one is probably the best. And if you want to make it visual and match, potentially sacrificing some of the safety, the second strategy works well. These are operations, this expression is available on, you can do number.expression, image.expression. It's the same language. There are things like square root, pi is defined in there. It's a bonus programming language. Yeah, there's no significant performance difference between these approaches. Question? Yeah. The question is NDVI only defined on Landsat? And the answer is no. It's a ratio of near infrared to infrared. And so it's defined on anything that measures near infrared and red. Near infrared and red. So it works on Sentinel. It's different bands. They divide up the electromagnetic spectrum differently, and you'll get different results, but the underlying strategy is the same. And there's a handful of these. There's like normalized difference, water index. Yeah, there's a lot there. Okay, I'm gonna blitz. We have 3 minutes. If you have questions, just throw them up. We can do charts is the whole idea here. We have a point that we're sampling, and we are able to generate a chart from that. And this is a time series of a collection for this particular observation. Again, NDVI over time. If we want to reduce, Katie mentioned the zonal statistics and reducing regions. I'm sorry, this is such a blitz. This is usually a 4-hour course. We can look within a particular region and get information about sets of values in that region. Okay, sorry, let me just uncomment this. Part of the value here is you get to bring home, whoa! All right, I will go through this really quickly. When you're doing a reduction, so I'm skipping all the way to the end. When you're doing a reduction, you are computing over potentially very many pixels. We have this parameter, well, when you try to do it and you specify too many pixels, you're looking at a really big region, you'll get an error message that says, you're doing too much. We found this many pixels, and max pixels only allows this many. I think it's 10 million, if I can count correctly. We call it a blade guard. So if you've ever used like a electrical saw or like a table saw, there's a safety feature that you can remove if you're really careful and you know what you're doing. And that's basically what this is. We're saying, if you are comfortable, if you think this is okay, you can specify that many max pixels. And so we can even be a bit liberal and say this is 1 billion. And if I rerun this, this is just a safety mechanism so that I don't end up accidentally trying to do processing over 500 quadrillion pixels because I specified the wrong scale. This is a way of doing kind of a sanity check, a proofing of whether this is whether this is reasonable to expect. Okay, and I won't go into all the details here. We're at time. Just know that max pixels is our blade guard, and you should not sit here and I've seen people do this. Please don't do this. This helps no one. If you send me a script and say, oh, why doesn't this work? It's because you're not thinking about the limits. And so this, if I see this, I'm probably not going to answer your email. Yes, please think about the limits. Think about things like scale. Scale is always in meters. Everywhere you see scale, it's always in meters in Earth Engine. And max pixels and error margins, think about them as you write your code. Question?
Yeah, is there a recording of the 4-hour course somewhere?
Yes. If you search Earth Engine 101, you should find a longer recording of this. Yeah. How you doing? Any other questions? I am super appreciative that everybody came here today and filled their brains with Earth Engine. If you do have questions, we will all be around this week. Thank you very much. Please enjoy your Earth Engine coding.